So I squared both sides.
That's a good move.
Oh my god, my memory's so rusty on this. Golly.
No, but it's normal. You haven't done it in a while. So yeah, you squared both sides. So wait, what letters did you use first of all?
P and Q.
Okay, cool. So let's go on the
So 2pq squared equals... No, so 2q squared is p squared.
So assume the square root of 2 is equal to p over q, and specifically where p and q are integers and the highest common factor of p and q, p and q equals 1. So you've squared both sides. So you've said 2 equals p squared over q squared. And so I'm just, writing out what you've said so far. Did you do anything else after?
Then I times both sides by q squared.
Okay. So 2q squared equals p squared.
And that means that p has to be even. No?
Okay. Yeah, so p has to be even. Do you know why? Like, do you know what the reasoning is?
Because of the 2q squared.
Yeah. So specifically well, first of all, we have to say p squared has to be even.
Oh yeah, sorry.
Yeah, but you're right. No, you're right. What you said was correct. So p squared is even, therefore p is even, because an odd number squared would give you an odd number, so therefore p has to be even. It's just giving the extra reasoning. So, therefore p squared is even, therefore p is even. So if p is even, then we can say that p is equal to like 2m, where m is an integer. This is just me laying it out like step by step. So yeah, before I say what we'll do, maybe you might be able to guess what the next step might be.
Would you do 2n plus 1 because q is odd?
Well, that's the question.
No, that's the same one.
Well, if we've just used the fact that p equals 2m, or if I've just mentioned or introduced the fact that p is equal to 2m, i.e. it's even, how can we now use that in our main body of work?
Square root of 2 equals 2m divided by q.
Well, okay, you're thinking along the right lines. Rather than substituting it there, you can substitute it on the third line, like the 2q squared equals p equals 2m brackets squared.
Okay.
And just reminding ourselves, oh, bless you.
Sorry, thanks.
It's all good. Just reminding ourselves, we are doing a proof by contradiction. So at some stage, we're going to find something that just completely crumbles. So, in fact, maybe if I tell you what we're trying to get to, you might be able to get to it. In this particular proof, the breakdown happens by showing that we've shown P is even, but we end up also showing that Q must be even, which is a contradiction because the highest common factor of P and Q is supposed to be 1. But if they're both even, that means they both have 2 as a common factor. So if you can convince me that Q is also even, then you've done the main body of work?
Q is also even.
How do we like?
Could you like expand 2m squared to 4m squared?
Mm-hmm.
And then if you divide by 2, q squared equals 2m squared. And that proves that q is even.
Perfect. That's it. Yeah. Let's write that down. So, 2q squared equals 2m bracket squared. 2q squared equals 4m squared. Q squared equals 2m squared because we're dividing by 2, like you said. So therefore, q squared is even. Therefore, q is even. But HCF of P and Q equals 1. So contradiction. So it must mean that our initial assumption that root 2 is equal to a whole number divided by a whole number, where P and Q have a highest common factor of 1, that must have been wrong. Therefore, we've proved by contradiction that square root of 2 is irrational. So, how do you feel about that?
Good. I really do understand it.
That's good. Okay, so now I'm going to ask you, can we extend it to, can you now that you've got a template for square root of 2, can you prove by contradiction that the square root of 3 is irrational? So prove
Nope.
that the square root of 3 is irrational. And that's on second slide.
I'm watching through the
screen share.
Okay, so assuming that square root of 3 is rational, do we do the same things but with odd, that both are odd?
Well, here's a question. What does it mean for a number to be a multiple of 2?
Divisible by 2.
Oh, so I just gave it away. I was meant to say, what does it mean for a number to be even? And then it means it's a multiple of 2. So in this case, we're trying to show that they're both multiples of 3.
Okay, so I got 3q squared is 9z squared. Well, let me just slow down.
I think I can guess where you started, but yeah, if you can say where you how you started.
I started the same as the first one, so square root of 3 is p over q, and then 3 is p squared over q squared.
Okay, so assume the square root of 3 equals p over q, where p and q are integers, and the highest common factor of p and q equals 1. Then 3 equals p squared over q squared. Then 3q squared equals p squared.
Mm-hmm.
And then you said, therefore, p
squared has to be divisible by 3.
Yep. So here's a neat way of writing it. 3 is a factor of p squared. Therefore, 3 is also a factor of p. Therefore, p equals, you said 3z, right?
Yeah.
3z, where z is an integer. And then?
3q squared equals 9z squared. And then
yep.
So, squared is 3z squared.
Equals 9z squared. Therefore, q squared equals 3z squared. And then what did you say after that?
3 is a factor of q squared, so 3 is a factor of q.
Yep, 3 is a factor of q squared. Therefore, 3 is a factor of q, but
that doesn't prove. Right?
Pardon?
That doesn't prove it's odd though.
It's not about proving that it's odd. What it does do is it disproves the fact that the highest common factor, it goes against the fact that the highest common factor is 1. Yeah, the highest common factor of P and Q equals 1. But, if they're both multiples of 3.
Mm-hmm.
But also, three is a common factor. I've changed it up a little bit, but I'm just making the contradiction extra clear. Contradiction. So therefore, we've proved it's irrational. Does that make sense?
Mm-hmm.
And actually, yeah, any number. So you can prove that any number. So, for example, the square root of 5, we can prove that that's irrational. And we show that the two numbers P and Q are both multiples of 5.
Mm-hmm.
The square root of 7, for the same reason, we show they're both multiples of 7, and so on and so forth. And actually, it can build up to a general proof that the square root of n, where n is not a square number, must always be irrational. And actually, you can even extend it to say that the cube root of 3, for example, must be irrational. And you can use similar arguments there as well. So, yeah.